Yesterday and earlier today, we defined radioactivity as a natural process, as a random process whereby a nucleus decays. I want to define something else now called transmutation. There's a subtle difference between transmutation and radioactivity. Sounds the same, almost. Transmutation is the conversion of one element to the other. Radioactivity is a natural process of decay. What's the difference? Transmutation is the actual conversion. Radioactivity is one mechanism among several that can cause transmutation. So radioactivity, the decay, can cause one element to change into another, can cause transmutation. Nuclear fission, which we'll talk about in a couple of days, same thing. Nuclear fusion, same thing. It's a process that can cause transmutation. Radioactivity is natural, and it can cause transmutation. Now, we're going to describe the transmutation of one element to another by nuclear equations. These are in some ways like a chemical equation. In a chemical equation, you have a reactant side and a product side, and you want to balance the number of hydrogens, let's say, and the number of oxygens and the number of sodiums on both sides. We're going to have two sides in a nuclear equation as well, but because we're not dealing with chemical interactions of electrons, basically, we're dealing with nuclei, we're not balancing the number of atoms of something. Rather, we're balancing the number of, we call them nucleons, the number of protons and neutrons. Best way to do this, best way to show you how to do this is with some examples here. First one says, write the nuclear equation for the transmutation of radium-226 undergoing alpha decay. Here's radium-226. It undergoes alpha decay. If it undergoes alpha decay, it means it's producing an alpha particle. We don't put it on the left-hand side, because then it wouldn't be producing an alpha particle, it would be absorbing an alpha particle. And that can happen sometimes, but that's not radioactivity. That's a whole other process. Radium-226, we could call, if you want to think in terms of chemistry terms, we could call it a reactant. Sometimes, more often in physics, we call it our parent nucleus. The parent is what we start with. What do we end up with? Well, if we're talking about chemistry terms, we would end up with the product or the products. But if we use nuclear physics terms, we would usually call it not the product, not the parent. It's kind of a sexist thing. We don't call it the kids, we call it the daughter nucleus.
Oh, that's cool. I don't really think that was an own game moment. We're not breaking any social grounds here.
We call it the daughter nucleus. Okay, the parent nucleus generates a daughter nucleus, most likely because it knows that daughters are going to be less of a pain in the butt than sons will be. So what is the other daughter nucleus produced here? Radium-226 decays into an alpha particle plus what? Well, we got to balance not the radiums, not the alphas, but rather we have to balance the protons and neutrons. So let's count up. On the left-hand side, we have 226 protons and neutrons. On the right-hand side, we have, well, 4 in the alpha particle. What's left over? 222. 4 plus 222 is 226. We had 88 protons. Now we have, well, we have to have 88 on the right side. 2 of them were taken by the alpha particle. How many do we have left? 86. If you check your periodic table, you'll find that that atomic number 86 is radon. Now, just because we've illustrated a nuclear reaction, a radioactive decay reaction here, where radium decays into radon, that parent decays into this daughter, that doesn't mean that radon is not radioactive. It can itself decay because it's not stable. Alberta has a large amount of radon gas, radioactive radon gas, in soil, more so than most of the rest of the world. That's why you hear on the radio all the time ads for for companies that will check your basement for radon gas. The idea is this: you dig a basement. If there's a lot of radon gas in the area and you have cracks in your basement, then that radon gas can seep through and your basement can essentially be radioactive. Different companies will check for that and then remediate your basement so that it ends up being safe. That radon gas is radioactive. You breathe in that radon gas, it decays and produces ionizing radiation. It can do damage to you, right? All right, so there's the first reaction. Let's take a look at another one here. Example number 2. So to write the nuclear equation for the transmutation of a radioactive isotope lead-214 undergoing beta-negative decay. So we start with lead-214. It's not stable because we have too many neutrons. So we produce a beta particle. What's the parent here? Yeah, lead-214, the parent, the reactant. What else is produced as a result of this beta-negative decay? This neutron changing into a proton and an electron. 0 plus what is 214? 214. Now watch this. This is one of the most common mistakes made in this entire unit. -1 plus what is 82? 83. What do you think people often mix up and make that? No, not 82, 81. People will often write that as an 81. 83, if you look at your periodic table, is bismuth. So the daughter nucleus here would be bismuth. Now watch this. There's also something else produced here. You don't have to figure that out in this case. You just have to remember that every time you have beta-negative decay, every single time, you also produce something called an antineutrino. No, they're not. No. A guy named Wolfgang Pauli, almost 100 years ago, looked at this and said, things aren't quite right. The energy just doesn't quite work in this reaction. So there's got to be something else, a neutrino or an antineutrino, depending upon the reaction. He didn't have any proof for that, but the math worked. We now have proof for it. We now know that neutrinos and antineutrinos do exist and that antineutrinos are produced as a result of beta-negative decay. One of the places they do a lot of research on neutrinos and antineutrinos is actually in Canada. If you've ever driven through or past Sudbury, Ontario, anybody driven? Yes? What's Sudbury, Ontario famous for? Do you know? Nickel. They mine nickel in Sudbury, Ontario. They have these nickel mines that are kilometers deep, kilometers under the rock. Sudbury, Ontario is also famous for. Every town has the world's largest something, right? Vegreville has the world's largest Ukrainian Easter egg. This town in New Brunswick has the world's largest potato. Sudbury has the world's largest nickel. They have this big nickel up on a hill, except it's made out of plywood. You got all this nickel in Sudbury, and they build this world's largest nickel out of cheap plywood. Cheesiest thing ever. It is. It really is. Yeah, I don't know if that's the world's largest one or not, but maybe. But in Sudbury, they have these nickel mines that are kilometers deep. Nothing gets in there. It's so insulated from the rest of the world because it's so deep. Nothing can make it through all that rock, kilometers of rock deep, except for neutrinos and antineutrinos. So you're isolated from the rest of the world except for neutrinos and antineutrinos. The neutrinos and antineutrinos can penetrate through that rock kilometers deep. You got millions of them going through your body right now. They can penetrate this rock kilometers deep, and then they can be observed in this observatory that's insulated from the rest of the world because of how deep it is. So they do all this research in Sudbury because they have these mines in Sudbury that some of them aren't being used anymore.
So whenever it's
Go ahead.
-1.
Yes, whenever it's 0 - 1, beta-negative decay, you always get an antineutrino produced. You don't need to worry about balancing anything. You just got to remember that with beta-negative decay, an antineutrino is produced. Let's take a look at another one. Let's say this time we have magnesium-23 undergoing beta-positive decay. This would be 0 + 1b, or Parker, you could have said 0 + 1e. Exactly the same thing. What else is produced here? Well, 0 plus what is 23? 23. World's easiest math question. 0 plus 23 is 23. 1 plus what is 12? Yeah, this is 11, right? This one was, you had to be careful with the addition, right? Because it was a minus. This one's a bit easier because it's a plus. 1 plus 11 is 12. 1 plus 11 is 12. Yes, it is.
Oh. Yeah, 12 minus 1, right? Can we do minus?
You can do minus. 1 plus 11 is 12, or 12 minus 1 is 11. Atomic number 11, if you look in the periodic table, is sodium Na. Take a guess at what else is produced here. Yeah, not an antineutrino, but just a neutrino. So beta negative always produces an antineutrino. Beta positive always produces a neutrino. And that's just you just got to remember that. Simple as that. Here's the way I remember which is which. To me, anti kind of connotates a negative, reverse, backwards. Antineutrino goes with beta negative. Neutrino goes with beta positive. As soon as I see the anti, I don't remember necessarily neutrino goes with positive. I remember anti goes with negative. And then the other one has to be by process of elimination. Example number 4, part A. Complete the following nuclear equations. This is kind of backwards, right? We're not saying what it is. We're working backwards here. 30 plus what is equal to 30? Jacob, 30 plus what is equal to 30? 0. Excellent, Jacob. 16 plus what is equal to 15?
1.
Negative 1. 16 plus negative 1 is equal to 15. What's 0 minus 1? 0 minus 1, the particle is? You could say it's a beta particle, right? You could also say it's an electron. Let's write it as an electron this time. It's exactly the same thing. Just two different ways of writing it, right? Anything else? Yeah, this is an antineutrino because it's a beta negative. Next one. 238. 234 plus what is equal to 238? Oh, the math is hard now, isn't it? 4. 90 plus what is equal to 92? 2. What's that? It's an alpha particle, or we could call it a helium nucleus, either one. Same thing. Anything else produced there? Nope. That's it. 13 plus 0 is 13. 6 plus 7 minus 6 is plus 1, not minus 1. 0 plus 1 is a positron. We could write that 0, 1 E or 0, 1 beta. Anything else? Yeah. There's a neutrino there as well. It's a symbol. And last example, and we are done. Complete the following nuclear artificial transmutation. Listen, we talked about radioactivity yesterday and earlier today. We said that radioactivity can result in transmutation, but there's other things that can result in transmutation as well, including some things that we can cause. It's not radioactivity, but it still results in transmutation. If we bombard nitrogen with an alpha particle, then you can actually sometimes fuse together the nitrogen and the alpha particle and produce something else. So this is not alpha decay because the alpha particle is not on the daughter side, on the product side. It's on the reactant side. The alpha particle becomes part of the reactants. In order to figure out what else is produced on the right-hand side, we've got to figure out what's on the left. 14 plus 4 is 18. 7 plus 2 is 9. All right. 17 plus what is 18? 1. 8 plus what is 9? What's this? You could say it's a hydrogen nucleus, or you could just say it's a proton. It's exactly the same thing, right? A normal hydrogen nucleus has 1 proton and no neutrons. So it's a hydrogen nucleus or it's a proton, whatever you want. Next one. 105 plus 0 is 105. 48 plus minus 1 is 47. And that's going to be Ag, silver. It's called the electron capture, when an electron is captured by the nucleus, absorbed by the nucleus. I would like you now to have a look at worksheet number 24. You want the bad news or the good news?
Bad news, there's going to be a lot of questions. Good news, they're short.
Nailed it. It's like 12 questions. That's the bad news. The good news is, I think there's 14 questions actually. That's the bad news. The good news is it should take you like 5 to 7 minutes to do all 14 questions.
I like